Why, hello there, everyone. How nice of you to join me today on Lesson 1, Review of Exponential and Logarithmic Functions, as we begin this unit, Exponential and Logarithmic Functions, but with calculus. So let's take a look and remind ourselves what exponential and logarithmic functions are. First off, an exponential function is basically any function that can be written in the form y equals a times b to the power of x, and where a is some coefficient, b is the base, and our variable is our exponent. A logarithmic function is a function that are the inverse of an exponential function. So if I have that x is equal to a b to the power of y, then I have that y is equal to log base b of x over a. These should be familiar with you from Math 30. This is just a quick look at what their graphs look like, what exponential and logarithmic curves look like. Not that those are in any way relevant to our current circumstances. Yeah. Anyway, so let's talk about converting between exponential and logarithmic forms. So remember, the key is that a to the n is equal to m, means that n is equal to log based a of m. Okay? I find that it's always easier to just see it with numbers. So let's say I have 5 to the power of x is equal to 45, and I want to solve for x. So what I'm going to do is convert it to log form. So this means that x is equal to log base 5 of 45. So you can see all the components are there. 45. The base. So it's nice because the base of the exponent is also the base of the log. And the exponent itself becomes the answer. Yeah, it's the same color. I'm trying to be all color codey here, and it's backfiring a little bit. There we go. See? Now we see it. All right, so I can, if I want, take this a step further. If I wanted to use a calculator to actually calculate the number x, let's assume that I actually care about using a calculator, which we all know I don't. I don't like using calculators. But if I wanted to, and if I happen to have a really old calculator that doesn't have a log base function, like I have a classic TI-83, then I can use this system where I can just do log of 45 divided by log of 5. And that would be approximately 2.3652, which I care less about because, again, I don't care about calculators. It's this part at the beginning that I care about. All right, let's try another one. Log base 2 of x is equal to 3. So, yet again, we've got the base of the log becomes the base of our power. And then the answer, the thing at the end there, becomes our exponent. And that is equal to x. We have 2 to the 3 is equal to x, which tells us that x is equal to 8. Hooray! That one didn't need a calculator at all. Ha ha ha. Okay. These ones are pretty quick, so I'm going to do them pretty quick. We have 10 to the power of some value. I'm going to say that this is equal to x is equal to 100, which means x must be equal to 10. Because 10 to the power of 10 10 to the power of 10 isn't 100, Miss Neufeld. You crazy. 10 to the power of 2 is 100. See? Accidents happen, children. Accidents happen. X is equal to 2. All right, so then we have log base 2 of 32. I'm going to again set that equal to x. We have 2 to the power of x is equal to 32. X is equal to 5. There we go. And yeah, no, I'm totally not going to go fix that flub in post. I could, and I choose not to. All right, so that's how we convert between logarithmic form and exponential form. Now, let's actually play a bit with log rules. These, again, should be familiar. The log of a product is the same as the sum of the log of the two factors of that product. Same thing with quotients, except subtraction. We can take the power of a number in a log and put that out front as a coefficient. The log base a of a is 1, so which makes a lot of sense because that's, coming from the idea that a to the power of 1 equals a. That checks out. The log base a of 1 is always 0, which again makes sense because that's the idea that a to the power of 0 is 1. Log base a of a to the n is just n, because that comes from the idea that a to the power of n is a to the n. And then a to the power of log base a of n is just n, because they're inverse operations. So if you go to the power of log base a of n of a, it's just going to cancel out, and all you'll be left with is n. Also, we have that log base a of b is equal to log base c of b over log base c of a. So we can divide that out. That's the same way we use our calculators to calculate when we don't have that base function. So rewrite log x to plus 3 to the power of 2 divided by x times the square root of x minus 1 as a sum and difference of logarithms. So I'm just going to break this down one piece at a time. So I'll start with log x plus 3 squared. I'm just rewriting it right now, just because I can. Square root of x minus 1. So I'm going to break this down first into its difference. So it's a division statement, so I can break this down to subtraction. So this is going to be log of x plus 3 squared minus log of everything in the denominator, x times x minus 1 to the 1/2. So that's that quotient rule for logarithms. Then I'm going to take out the exponent there. So log x plus 3 all to the power of 2, that just becomes 2 log of x plus 3. And I'm also going to split up the product on the interior of that second logarithm. So this is going to be log of x plus log of x minus 1 to the 1/2. So I'm just splitting that up using that product rule for logarithms. And then this becomes 2 log of x plus 3. I'm going to break this up, distribute the negative, minus log of x, and then I'm going to take down that exponent, minus 1/2 log of x minus 1. And there you go, fully expanded. Don't mind the kitten sounds in the background. She is just upset that I'm paying more attention to math than her, as usual. All right, natural logarithms. Okay, natural logarithms are really interesting because they're just logs, regular old logs, but they use Euler's number as the base of the logarithm. So Euler's number is this really nifty number that's useful for a whole bunch of things that I'm not going to get into right now, but suffice it to say it's this number. It's gotten from the limit as x goes to infinity of 1 plus 1 over x all to the power of x. And natural logarithms are just the log base e of x. That's natural log of x. So instead of writing log base e of x all the time, we just have this separate notation, natural logarithm, ln. Properties of natural logs are, well, pretty much the same as properties of regular logs, because natural logarithms are logs. They have all the same rules. So y to the ln of x is x to the x equals e to the power of y. Makes sense, because e is the base. Ln of e to the x is equal to x. Again, because it's log base e of e to the x, and by log rules, that's just x. E to the power of natural logarithm x is just x, same as the regular log rule. Ln of e is 1, and ln of 1 is 0. I'm going to call it ln a lot. Just get used to that. Instead of natural logarithm all the time, I'll often just refer to it as ln. All right, so not like lawn like your grass, just like lawn like ln. Because I'm also not going to call it ln, because then I'll just start calling it Ellen. Oh my goodness, natural logarithms has a name, and it's Ellen. I'm kind of tempted to call it Ellen now. Anyway, so example 4. Determine the exact value of x, which satisfies the equation e to the power of 5 minus 3x equals 10. So let's do this. What we're going to do is I'm just going to again start by you know me, I like to rewrite the question. Fun fact, when I was in university, if I came across a question that I had no idea how to start, first thing I would always do is just rewrite the question. It helped me feel like I was productive and it got my brain stimulated. So what I'm going to do is I'm actually going to rewrite this using natural logarithms. So I'm going to say that ln of e, or ln, e to the 5 minus 3x. So I'm just going to take each of both sides. I'm going to take the natural logarithm of. Oh, wow, I wrote that as an exponent. I don't know why. Natural logarithms can't have exponents. That's not a thing. Oh, God, this is terrible. I'm starting this again. So first thing I'm going to do is I'm going to take the natural log of both sides. You know how we love doing opposite sides. In algebra, it's great. So recall, it says real. Recall that log base a of a to the m is just equal to m. So remember, that means that ln of e to the m is m. Just a little reminder. I'm using different variables this time just to shake things up. So what that tells you is that the natural log of e to the power of 5 minus 3x is just 5 minus 3x is equal to ln 10. So what I can do now is just isolate for x, like I always normally do. So this is ln of 10 minus 5, and x is equal to ln 10 minus 5 all over negative 3, or a better way of writing it, divide out the negatives there, and I get 5 minus natural log of 10 all over 3. Bada boom. Done. All right. So getting really comfortable with your log laws is really important for this. Review log laws if you don't remember them. They're really important. Log and natural log rules are really important that you remember. So determine y if natural log of y is equal to 2 times the natural log of x plus 1 minus 1/2 the natural log of x minus 3 the natural log of x minus 2. Whew. Okay, so honestly, I'm just going to be playing around with this using log laws. Every time I say log laws, I think of Loblaws, like the grocery store conglomerate. And I don't know why I needed to tell you that in this video, but I felt like I did, and I don't have any regrets, and I refuse to apologize for doing so. All right, here we go. So as usual, I've started by just rewriting everything out. Then what I'm going to have is that this is the natural log of x plus 1 squared. So this is like that earlier example, but I'm doing it backwards. So now I'm going to say, hey, I can factor out that negative there and make this ln of x to the 1/2, right? We know from our exponent laws there, plus ln of x minus 2, that's a 3, to the power of 3. Banana syndrome, you know? So that means ln of y, using my product quotient rules here, is the natural log of x plus 1 squared divided by the square root of x, because that's x to the 1/2, times x minus 2 cubed. So that's, again, just using my log laws. But now what I can do is take each side and raise it as an exponent of e. This is a nifty trick for getting rid of natural logs, by the way. If you're trying to get rid of the natural log, just like put it as the exponent with the base of e. Easy peasy. The reason we can do that is obviously if e of something equals e of something else, like for example, if we know e to the a equals e to the b, then it follows that a equals b, right? That's pretty logical. So now I have the natural log of x plus 1 all squared all over the square root of x times x minus 2 cubed. All right, now that I've got that, we finished this off. We know from before that e to the natural log of y should just be y. That's something we should also know just from our log rules. So this becomes y is equal to, well, the same thing applies here. E to the natural log of x plus 1 squared over the square root of x times x minus 2 cubed is just going to be what's on the inside of that natural logarithm. X plus 1 squared all over the square root of x times x minus 2 cubed. And we're done. Ha 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 ha. All right. So get some practice on this. If you're not super comfortable with logs, get comfortable with them, because if we're going to be able to work with them in derivatives and moving forward, you're going to need to get comfortable with them. All right. Peace.